Here is a short demo for preprocessing the TrackML dataset running in a Jupyter notebook. First, we import all the necessary Python packages for matrix operations and data visualization, such as NumPy, Pandas, and Matplotlib. We also use the TrackML library that is provided by the organizers of the TrackML challenge to conveniently load hadron collision events data. Let's use the load event function here to load just one of the events data to see what the raw dataset looks like. As we can see here, each event has 4 different datasets: hits, cells, particles, and ground truth. The hits dataset gives you the coordinates where a detector cell senses a particle passing through the detector layer. Here is a graph showing all the hits locations. The color of the hits represents the different detector layers. The ground truth dataset assigns a particle ID to every hits. A track can then be constructed by connecting every hits that belongs to the same particle. Our goal for data preprocessing step is to convert the hits location into pixels of an image. We can then utilize the computer vision approach to let the computer look at the image and figure out the correlation among every pixels or hits so that it can cluster those hits that might be on the same track. The first step is to convert the original XYZ coordinates to r theta phi, or the spherical coordinates. The r coordinate here represents the distance between a hit and the center of the detector, near where the hadron collision occurs. Let's run it once and see how the hits data looks now. As we can see here, the hits are separated into multiple layers based on the r coordinates, and we found out that there are total 48 different layers. To make the data become the image form we needed, we converted the 3 coordinates again into 3 indices of a 3D array. Just like in normal image data, our data will have height, width, and depth 3 axes. Although for a normal image, the depth axis is usually just the RGB 3 channels. Our data will have 48 channels due to the 48 different layers. Here we set the height and the width both to be 2048 to avoid any one of the hits overlapping on other ones. And we set the density argument here so that it won't plot all of the 100,000 hits on the same graph. Let's now create and plot the resulting 3D array. By just visually inspecting this graph, we can already observe some short tracks formed by those adjacent hits. And machine learning algorithms, such as CNN, may further help us with identifying all the particle tracks faster and more accurately. But before that, we divided the entire data array into smaller arrays with a sliding window. Since the original data array is way too big to fit into our CNN models. Now, let's run the entire code and save them into files.